Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Network Function Virtualization, often abbreviated as NFV, represents a significant shift in how network services are delivered and managed. Traditionally, network functionality, such as routing, firewalls, load balancing, and packet inspection, has been tied directly to proprietary hardware appliances. These devices were static, required manual configuration, and often came with significant overhead in terms of physical space, power, and lifecycle management. NFV challenges this model by abstracting these functions from the hardware, allowing them to run as software instances on general-purpose servers or virtualized platforms. The core purpose of NFV is to decouple network functions from dedicated hardware. Instead of purchasing a physical firewall appliance, for example, organizations can now deploy a virtual firewall as part of their data center or cloud infrastructure. These services can be instantiated on demand, scaled dynamically, moved across different environments, and decommissioned when no longer needed. This level of flexibility has made NFV central to modern network design, particularly in CloudNet, service provider, and enterprise environments that demand agility. For Network Plus certification candidates, NFV is part of the virtualization and infrastructure objectives and may also appear under emerging technologies. While the exam avoids vendor-specific implementations, it does require a conceptual understanding of what NFV is, why it matters, and how it interacts with other network components. You may encounter scenario-based questions that ask you to choose between deploying a physical device or a virtual function, or to troubleshoot a virtualized network service within a broader infrastructure. At its foundation, NFV operates by running network functions as virtual instances rather than on fixed hardware. These functions might include firewalls, load balancers, WAN optimizers, or even DNS and DHCP services. Each of these can be packaged as a virtual appliance, container, or cloud navic service, and then deployed on demand using virtual infrastructure. This approach allows for consistent performance, rapid provisioning, and location-independent operation, whether the services are running in a data center, private cloud, or public cloud platform. There are many practical examples of virtualized network functions. A virtual firewall might filter traffic between VLANs inside a hypervisor. A virtual load balancer can distribute web traffic across multiple virtual machines in a cloud environment. Virtual routers can provide IP routing between different virtual networks or sites. WAN optimization appliances can now be deployed as software instead of physical branch devices. DNS and DHCP services, once reliant on fixed on-prem servers, can now run as flexible virtualized instances, even in multi-tenant or hybrid networks. NFV infrastructure requirements include several layers of virtualization technology. Virtual machines or containers host the network functions themselves. A hypervisor or container runtime manages their execution. Virtual switches and routers enable connectivity between them, while orchestration platforms coordinate their deployment, scaling, and removal. These orchestration tools may include platforms like OpenStack, Kubernetes, or VMware vRealize depending on the environment. Without this supporting infrastructure, NFV cannot deliver the automation and scalability it promises. Compared to traditional hardware, NFV is faster to deploy and easier to modify. New services can be provisioned with a few lines of code or a few clicks in a management console. There's no need to rack a physical appliance, connect cables, or schedule maintenance windows for installation. NFV also reduces the physical footprint of a network environment, less power, less cooling, and fewer points of physical failure. Scalability becomes simpler. Instead of adding new hardware, administrators can deploy additional virtual instances as needed. NFV offers a number of operational benefits. Rapid provisioning means that new services can be deployed in minutes instead of days. Virtual services can be spun up to support temporary projects or scaled back when demand decreases. Physical maintenance, such as replacing failed devices or upgrading firmware, is significantly reduced, since virtual functions can be updated via software patches and version upgrades. And because services are software-defined, they can be integrated with automation tools to enable programmatic control and orchestration across the entire network. NFV is closely aligned with software-defined networking, SDN, another key trend in modern network architecture. While SDN focuses on separating the control plane from the data plane and centralizing network policy, NFV focuses on virtualizing the network functions themselves. In combination, SDN provides the brains of the operation, making decisions and enforcing policy, while NFV provides the muscle, delivering the services that route, filter, and optimize the data. Many orchestration systems tie both SDN and NFV components together into a single platform for unified control. Elasticity and automation are central to the promise of NFV. Services can grow or shrink as needed, based on traffic patterns, business needs, or security requirements. For example, an intrusion detection system can be scaled up during high traffic periods and scaled back during off hours. Automation platforms monitor demand and trigger these changes, ensuring optimal resource use. This elasticity supports highly dynamic workloads and makes NFV especially valuable in cloud environments, where agility and cost efficiency are paramount. One of the more subtle benefits of NFV is location independence. Because virtual network functions are not tied to specific hardware, they can be moved from one location to another as long as computing resources are available. A load balancer could be moved from one data center to another for disaster recovery. A firewall could be spun up in a branch office for local traffic inspection. Functions can also be instantiated in the cloud, closer to the users or applications they support. This makes NFV a key enabler of distributed, scalable network architectures. The use of APIs and templates is another reason NFV is so powerful. Instead of relying on manual configuration, services can be defined in code, declaring how they should be deployed, what resources they need, and how they connect to other components. These templates can be reused to create identical services in different environments or at different times. APIs allow integration with DevOps pipelines, enabling automated deployment of network services alongside applications. This promotes a new way of thinking about infrastructure as code, programmable and repeatable. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. While Network Function Virtualization offers flexibility and scalability, its performance is tightly linked to how resources are allocated and managed within the host system. Because NFV services run as virtual machines or containers, they share CPU cycles, memory, and I/O bandwidth with other workloads. Poor resource planning can cause degraded performance or even service interruptions. In particular, network input/output, I/O, can become a bottleneck if the virtual NICs, virtual switches, or hypervisor platform are not optimized. In high-throughput environments, administrators may employ hardware acceleration, such as SRIOV, single-root I/O virtualization, to bypass software switching layers and improve packet handling. Monitoring and visibility tools play a critical role in maintaining NFV environments. Unlike traditional physical appliances that may be monitored using proprietary interfaces, NFV functions are often managed using platform-agnostic tools that collect metrics from multiple layers of the virtual stack. Health and performance data, including CPU usage, memory allocation, packet flow, and error rates, can be gathered using agents inside the virtual machines or directly from the hypervisor. These metrics feed into alerting systems and dashboards, giving administrators insight into whether virtual functions are operating correctly or need attention. High availability is a key requirement in production networks, and NFV supports this through the use of redundancy, failover automation, and snapshot-based backup. A critical virtual function, such as a virtual router or firewall, can be configured with redundant instances across separate hosts. Orchestration platforms can automatically detect a failure and spin up a new instance, sometimes in a different data center, to maintain service continuity. Snapshot and cloning features allow for quick restore or rollback if a configuration error or software bug causes instability. Security in NFV environments presents unique challenges and opportunities. On the one hand, virtual functions can be isolated more easily than physical devices. Hypervisors can enforce strong segmentation between different functions, preventing one compromised VM from affecting others. Virtual firewalls and access control lists can be positioned dynamically, adjusted by scripts, or deployed with each new instance. On the other hand, because these functions run on shared infrastructure, strict controls must be in place to prevent lateral movement, data leakage, or privilege escalation. Security policy enforcement is often integrated directly into the orchestration layer, allowing centralized control of all network services. Lifecycle management is a cornerstone of successful NFV deployment. This refers to the full span of a network function's existence, from its initial deployment through ongoing maintenance to eventual decommissioning. Automated tools handle provisioning, ensure version control, and apply patches or updates in a controlled manner. These systems also archive logs, snapshots, and performance data to support rollback or forensic analysis. Lifecycle management makes NFV not only efficient, but also sustainable over the long term, reducing operational risk and improving consistency. NFV is widely deployed in a range of modern environments. In telecommunications, service providers use NFV to deliver customer services such as voice gateways, security appliances, and traffic shaping, all deployed as software rather than hardware. Enterprises use NFV in cloud NAPNEC architectures to spin up DNS, DHCP, and firewall services wherever they are needed. On-premises virtual clusters often run NFV components for edge routing, branch connectivity, or security policy enforcement, often as part of hybrid infrastructure that includes both physical and virtual assets. And the Network Plus exam, familiarity with NFV terminology and functionality is essential. Key terms such as virtual appliance, hypervisor, orchestration, and service chaining may appear in multiple choice or diagram-based questions. You may be asked to choose between virtual and physical deployment strategies, identify performance considerations, or troubleshoot a misconfigured NFV instance. Recognizing both the benefits and the trade-offs, such as ease of deployment versus complexity in management, will help you select the best answers with confidence. Despite its many advantages, NFV deployment is not without challenges. Orchestration complexity can be significant, especially in large environments where many services interact. Coordinating updates, maintaining consistent policies, and managing dependencies requires skill, experience, and sometimes specialized training. Resource conflicts, such as oversubscription of CPU or memory, can degrade performance or cause services to fail unexpectedly. Administrators must use performance profiling and alert thresholds to stay ahead of these issues. Additionally, staff may need to shift their focus from hardware management to automation, scripting, and virtual system design, a significant cultural and operational change. In summary, network function virtualization represents a powerful evolution in how network services are delivered. By shifting key functions from hardware to software, NFV enables rapid deployment, elastic scaling, and cost-effective management. It supports automation, policy-driven control, and the creation of dynamic network environments that can adapt to changing needs. While it introduces new operational complexities, the benefits of NFV far outweigh the challenges, making it a cornerstone of modern network engineering and a critical topic on the Network Plus exam and in real-world design. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.